At the abstract relationships. And really what this is we are looking at how one variable is affected by changing the other. And when I say changing, I mean like doubling, tripling, quadrupling, increasing it by 20%. This is a multiplication thing. It is very rare that we ever want to discuss what happens if I add 3 to the velocity or I subtract 10 from the acceleration. In life, we often increase things by percentages. We increase things by 50%. So we're multiplying something by 1.5. We're increasing something by 100%, which means we're doubling something. We're increasing something or decreasing something by 6%. We're multiplying by 1.06. Everything is multiplying or dividing, which is the same thing as just multiplying by something less than 1, and seeing how that change affects another variable. And so that's what this conversation really is. What happens when I do this to this variable? How is this variable affected if nothing else gets modified? So starting with an initial velocity of 0, what happens to the displacement if I triple the acceleration? Okay, and keeping my total time constant. So I'm not doing anything longer, so the time is the same. This term and this term are gone because they're just 0. And so the question is, I'm messing with this, right? If I triple the acceleration and keep everything else the same, what happens to x? Well, look, x and a are linearly related. This is x to the first power, this is a to the first power. Tripling the acceleration will triple the displacement. Now, if I tripled the time spent, I would end up multiplying the displacement by 9. That would, if I triple the time, since it's squared, I'm going to end up with 9 times the distance covered in that same scenario. But in this case, tripling the acceleration triples the distance traveled because a and x are both to the first power, meaning they are linearly related, right? In Algebra 2, you would say they are directly related. All right, this one's different. If I triple my stopping distance, how does that affect the initial velocity? So in both cases, I want to stop. So in both cases, I want the final velocity to be 0. In both cases, I'm not changing my acceleration rate. So I'm driving the same car, okay? And I'm tripling the distance I have to stop. So instead of trying to stop in 100 meters, I get 300 meters to stop. Okay, do we agree that if I triple the distance I get, I can actually drive faster at the beginning? So my initial velocity certainly goes up, but the question is, by what factor? And you got to see here, x is related to v squared. So if you triple x, you can only multiply v naught by the radical 3, because whatever factor you multiply v by, it gets squared before relating to x. V squared is related to x. So making x go up by 3, you can only increase v naught by radical 3. That's a square root relationship or square relationship. Just depends on what variable you're going to which way. All right, if I quadruple the time while keeping the acceleration constant, how much faster is my final velocity if I started at rest? Again, we are ignoring v naught. So what happens if I quadruple the time spent walking? How much faster am I? Quadruple. Quadrupling one quadruples the other. Why? Because they're linear related. Look, v is linear related to t. We're keeping the acceleration constant. We're not messing with it. We're just messing with the time. And how does it mess with the velocity? 4 times longer, 4 times faster, given everything else is the same. All right, this one, if I double my initial velocity and I don't change the distance, so I still want to stop in the same distance, and I'm still going to stop, so then my final velocity is 0. So I'm really just looking at how does v naught compare to a. If I'm going twice as fast, what does that do to my acceleration? If you multiply v naught by 2 and then square it, it's now 4 times bigger than normal, which means if you still want to stop, you need acceleration to be 4 times bigger. So doubling V naught quadruples A. Okay, think about that again. Whatever you do to V naught, it is a quadratic compared to A being some linear thing, some A to the first power. So doubling and then squaring it, 2 squared is 4, thus my acceleration required to make that happen has to be quadruple. All right, I dropped a rock from the building of height h, took t seconds. If I triple the height, how many seconds will it now take? Okay, so I'm dropping it and it's still going to the ground. So my final height here is 0. I'm dropping it, so V naught is 0. So I'm really looking at how does the height affect the drop time. Also, the acceleration is constant because it's still just under the influence of gravity. So the question is, what happens when I triple the height? Do I triple the time spent in the air? No. I think you can reason through that the rock's going to be going faster and faster and faster, so it's going to cover that extra distance faster and faster, so the time shouldn't triple. It turns out that this, in this case, h is related to t squared. So if you triple the height, you only have to multiply this by radical 3 because it's t squared. Multiplying t, right, making it square root of 3 times bigger and then squaring it creates a factor of 3. And that term now tripled and that term tripled, which means they're still balanced. Tripling the height does not triple the time it takes to fall. That would only be true if the thing was moving at a constant velocity. But this thing is accelerating, so it's going to get faster and faster and faster. So tripling the height does not triple the time. All right, we got a force. A certain force causes a mass to accelerate. This is Newton's second law, and just think about this. If I double the force, but I triple the mass, what acceleration is now produced? So now I'm actually messing with two things at the same time. If I double the force, I'm making the left side of the equation doubled, but I tripled the mass. So what should the acceleration do? Well, it has to go down by a factor of 2/3. Think about what happened to the left side of the equation. Didn't it double in size? Well, then the right side of the equation has to double in size. But since the mass went up by 3, the acceleration has to go down by the factor 2/3. 3 times 2/3 is 2. So if you do both of these things, mass going up by tripling and A going down by 2/3, that combination makes that side twice as big, and that's what happened when you made the force twice as big. Right, 7, I want to keep the mass constant and double the velocity. How much more kinetic energy, right? So this is kinetic energy is 1/2 mv squared. I'm keeping the mass constant, and I'm just doubling the velocity. Okay, how much more energy does this object have? Well, it turns out that the kinetic energy is related to v squared. So if you double the velocity, you actually quadruple the size of that term, and so then you've thus quadrupled the kinetic energy required to make that happen. Okay, Ke is related to v squared. If you mess with v, you square that factor to figure out how much more the kinetic energy would have been. All right, looking at 8. I double the length of the pendulum. How does it affect the period? Okay, so I'm not messing with gravity. We're still on Earth. 2 pi is just a constant. So I'm messing with the period. I'm messing with the length of the pendulum, and I want to know what happens to the period. Okay, so we're doubling the length of the period of the pendulum. We're making it, it was 5 meters, and now we're going to make it 10 meters. But look, T is proportional to the square root of L. Whatever you do to L, you end up taking a square root first before it actually affects the period. So if you double L, you actually only increase that side of the equation by radical 2, which means then the period of that thing will be radical 2. So lengthening the pendulum does make the period longer, but it's not the same factor. Doubling the length makes the period go up by radical 2. All right, this is some moment of inertia, which we'll discuss in a while, but if you have the formula, you can still think about things. If you double the mass and triple the radius, how much bigger is the object's moment of inertia? Well, you're doubling m, and you're tripling r, but r gets squared. So you're actually making r squared now 9 times bigger. You're making the mass twice as big. So you're actually making mr squared, 18 times bigger, because that's what 2 times 9 is. Thus, messing with the mass and the radius increases I by a factor of 18. You're going to see these double, triple questions every unit. The AP loves it. College professors love it. This is real world talk. We always want to analyze what happens to one variable if we mess with another variable. I can give you any physics equation you want. It doesn't even matter if you don't even know these equations, right? We haven't even talked about kinetic energy or pendulums or moments, and we haven't even really looked at forces yet. But if I give you an equation and I ask, if I do this to one variable, how will the other one be affected? That's always a double, triple type question. Sometimes, and I tried to give you examples, multiplying this factor by 4 creates a factor of 4 on this side. Sometimes multiplying this by 2 creates a factor of 4 because of a square relationship. Sometimes doubling this doesn't double the other side, doesn't quadruple the other side, and actually makes the other side go up by a factor of radical 2. And then occasionally messing with something makes the other thing go down, and that just depends on how the things are related. Whether they're on the same side of the equation, different side of the equation, subtraction sign, positive sign, and you got to think that through. Probably the first thing you can actually do is think about, okay, does increasing one increase or decrease the other? And that can maybe even get you started. But I would say most of the equations I've given you, increasing one quantity does increase the other quantity, but that's certainly not always true. I guess I could have given more examples of the other way, but this is kind of the only one. Okay.